point. Well, let K be a finite field, and we consider a projective plane over this field. Well, everybody knows that the Cremona group acts on P2 by birational automorphism. But we can consider some class of automorphisms which preserves K points. That is, if F in Cremona group we'll call birational permutation, if F and its inverse are defined and each point of P2 to P2K. Well, so it's quite easy to see that such birational permutations form a subgroup in the Cremona group. We will call this group B, Cremona 2K. Well, since our field is finite, the number of points, K points on projective plane, is finite. And since every element in this group is defined at each point of projective plane, of each K point of projective plane, we have a natural homomorphism from this group to the group of permutation of K points of our plane, which is isomorphic just to S this number of letters. So our question is, for which finite fields this homomorphism is subjective. Let's start finding answer for this question. So at first, we introduce the main method, how to prove this result for certain fields. The idea is there is a subgroup P gamma L2K in the group of, well, it's a problem. I think the problem that it's quite wet. 1 minute. Well, one more subgroup in our big group, B gamma L2 K, the symmetric group acting on the K points. This is a group such that permutations resolving collinearity. So
it contains EGL. And why is it 2?
2, this is just notation. So it's maybe quite strange since
because it contains PGL3 inside it, right?
Of course, yes. Next.
Very clever notation.
It's unclear, but it's not mine. We have the following sequence. Of course, when we have the action of automorphism group of projective plane, it preserves on all lines, and this preserves coordinations. And we have the following sequence of subgroups. And the main method is the following theorem by List and Bhattacharya. That let's consider a group G, such that this group contains linear transformation and is contained in our symmetric group. Then we have two possibilities. Either this group G is contained in our group preserving coordinations, or this group G contains alternative subgroup of symmetric group. So this is normal subgroup of symmetric group of index 2.
And so this has nothing to do with any birational geometry, right?
Not any birational geometry. The birational geometry will be soon. So,
and just in case, so anyway, this theorem by List and some other guy with a long name, so it was obtained earlier than any.
Yes, it's something like 70s, early 70s, or maybe even 60s. And so now we can apply this theorem, and to apply it and show that the image of our homomorphism is all symmetric group itself, we should find a birational permutation F, which satisfies two conditions. These conditions, that first condition, that F doesn't preserve collinearity, and the second condition is that F induced an odd permutation. In our symmetric group. So we see the first conditions give us that this case is impossible, since then our group doesn't preserve collinearity. And the second conditions show that image of our birational permutation in symmetric group is more than alternative group. Now we start.
Just to understand what is easy and what is difficult here. So if we wanted to show that our birational, our Cremona permutation group, if we wanted to show that our birational permutation group contains maybe not coincides with the whole symmetric group, but contains the alternating group, then after this combinatorial theorem, it's like more or less trivial, right?
Yes, it's
for this you just have to produce just any birational self-map given which is not isomorphism. Since it's not isomorphism, it's given by forms of degree higher than 1, and thus it cannot preserve collinearity.
But it can preserve collinearity on the set of k points. You see, it can trivially act on the set of k points, and then it of course preserves collinearity, since our group B gamma L2 is contained in symmetric group, not in Cremona group. So that's.
So I'm just trying to to ask the following. So suppose you found an element of the Crotone group which is given by forms of degree greater than 1.
Yes, yes.
Can it really preserve collinearity on the set of K points?
Of course can, since they, when we pass from our birational permutation to permutation of K points, we have huge kernel. So, of course, in this kernel, we have elements generated by polynomials of degree greater than 1.
We just preserves all the points as they are.
Yes, yes, it's trivial on the set of K points. But it's quite easy to construct element of birational permutation which doesn't preserve collinearity. It's simple part, and this is not so simple. It's interesting, and it can be do. It's not for all finite fields, this condition. Well, let's start our geometric construction of element F, which satisfies these two conditions. One. We consider a quadric in P3 with Picard rank 1. So it's something like sphere in our usual sense. Also, we consider a line which intersects this quadric in two conjugate points. Then, starting from this line, we can consider a family of planes which gives us a birational map from our quadric to P1. Sections of these planes are conics, so we have a structure, birational structure of conic bundles here. This conic bundle have two singular fibers corresponding to tangent planes passing through this line. So this is one singular fiber, and this is other singular fiber, and general fiber cuts a conic from our quadric. What is our aim? We want to construct birational self-map from Q to Q such that this will be P. G preserves fibers of pi, and on all fibers defined over K. G x3 billion except one where G x as odd permutation. So this is the first step of proof, and when we construct such self-map of Q. Then we can consider a pole, these points, we will call it N. And then by stereographic projection pass to projective plane. Then G induces a self-map of the projective plane, which preserves all K points on this plane and also acts on it as an odd permutation, which doesn't preserve collinearity. Is it clear, the method?
No, actually, I totally missed the details. So why do you, I see that you have the conic bundle.
Yes.
Now, what is the, did you already produce G small?
I'm not already producing. It's our goal to produce this G small.
So it's just a plan at the moment.
It's the most interesting part, how to produce.
So yeah, then I didn't miss the details. Then they just didn't appear.
Of course, yes. We just want to construct the G, and it is not possible for all finite fields. So we can see the plan here of our proof, and now we can start proving details. So, from now, for some time, assume that our field is of odd characteristic. Then we can write down the equation of this quadratic explicitly. It can be given by the following, where T is not square, which means that the Picard group has rank 1. Now our projection is given by just removing the first two coordinates in our projective space.
Andrei, may I ask a question just before we go into so precise details? So we know, well, basically, we know several simple examples of Cremon transformations, like the standard Cremon transformation, for instance. And okay, we don't. So basically, our plan is to produce some Cremon transformation with special properties.
Yes.
What if we check? What happens if we check just the most obvious ones? Do they all fail this task?
I
know one obvious candidate. I don't know about its properties, but it's just the simplest possible Cremon transformation that could possibly fit into this picture. So
Kostya, I think that it is difficult to construct. Suppose you take a quadratic transformation.
Yeah, let's take the quadratic.
You need such a transformation which preserves K points.
Yeah, sure. Just let's take our finite field. It has
consider to get not collinear points on the plane, and then consider quadratic transformations in centers within these points.
Yeah, so we take a Galois orbit of length 3, which definitely exists. And since just every Galois orbit of length 3 on a plane sits in a general position, I think it's very well. Okay, most of Galois orbits on the plane sit in general position.
Yes.
Then you just take the form of the quadratic transformation. The quadratic transformation centered in this Galois orbit.
Yes.
So what's the trouble here?
I think it's just even.
So is it even? If
it wasn't even, then anybody doesn't use construction like this, which I.
Well, I just, of course, we all believe that S.Cantat doesn't make simple mistakes, but well, I would say that we should always be in doubt that maybe he missed some simple information. So okay,
not only here, some other people,
but you didn't check that, right?
Some other people too resolving these problems, and they use also computer methods. So of course, I think the first thing that they checked, it's about this transformation.
So they, I mean, the other people like Susanna and others, they checked that this guy is an even transformation.
At least, yes, they checked it. Since
I see.
If we have elements of finite order, that is always, almost always they are even. So, for example, for characteristic 2 and Q greater than 2, it's proven that all transformation coming of finite order, coming from the Delpezzo surfaces, from conic balls, all there are even. So this is
very interesting.
Not a message here. So we should try more powerful things, not just so simple and naive. Okay.
So your coordinate is x, y, z, w, no?
Yes, x, y, z, w. Thank you, Victor.
And the projection to z and w.
Z and w, of course. Well, I'm usually use the t for the fourth coordinate, but here's t is not square. So projection for the w, of course. Well, and now we can construct the following automorphism of this quadric. Well, so x, y, z, w maps to alpha, depending on two variables, uv, plus t, where t is r naught squared, beta, uv, y plus, not plus, but then the next coordinate is beta, uv, x plus alpha, y, and two last coordinates just to be gamma uv on z and gamma uv on w. So what's the point here? It's about alpha and beta and gamma. Alpha, beta, and gamma are such functions here, and their numbers, which satisfies condition that they lie on conic given by the following equation. So U and V is just a rational parameterization of this conic. Of course, one can easily check that this conic has points, for example, 1, 0, 1, and therefore on this conic there is q plus 1 points. So the conic alpha square minus t beta square equals gamma square has q plus 1 points. For transformations like this, one can see that it's just a cycle group. So if you consider two different triples, alpha, beta, gamma, and compose such two transformations, you have a new transformation of this kind. And this will be a cyclic group. So if alpha, beta, and gamma are defined over K, so that they belongs to K, then we have cyclic group of order 2, Q plus 1. So, and since it's a cyclic group of order q plus 1, we can find two good elements in this group. So first element will be U0.
According to the trajectory coordinate length, the principal should always. Actually, in the light of that, it's possibly interesting to comment.
So very, I can't hear almost anything.
I'm very sorry. Was the question or just?
No.
No, I think it was not a question.
It's not a question. Okay, well, let's continue. So on this parameterization UV, we can find two special points. First is U0 V0, which corresponds to trivial map. So for these points, one has alpha equal to 1, beta equal to 0, and gamma is equal to 1. So actually, one can, gamma is never 0, 0, since if you put 0 here, this equation hasn't solution in K. Therefore, actually, we can don't think about gamma, put it 1 everything, and just divide alpha and beta on gamma. That's not a problem, and I think there will be a moment when I will forget about gamma at some point. Well, and the second special point on our projective line in UV is that corresponds to generator of our cyclic group. So actually,
Andrei, maybe one more question.
yes.
I just missed one detail at the very beginning. So, you are constructing some birational self-map. Is it going to be defined over the base field?
Yes.
And in the very definition, we were considering sure. Just in the very definition, we were considering everything defined over the finite field. And can you repeat what you said 5 minutes ago about elements of finite order?
But
do we know that all elements of finite order in our Cremona group don't solve this problem?
yes, but this
Yes or no?
This will be not element of finite order.
Ah, I see.
Oh, the constructed map will be not an element of finite order, but on K fibers, it will act trivially on all except one. And on the last one, it will be act as element of order Q plus 1. But on the fibers not defined over K, it acts like element of any big order. So it's not element of finite order itself, but in the restriction on K points, it has, of course, finite order since any element.
Yeah, because it's the restriction of K points is an image in the symmetric group.
Yes, yes.
Yeah, good.
So what do we do now? Now we want to use this U and V to do something with our transformation. What we can do? We can consider the map of projective lines. One will be projective line with coordinates Z and W, and it will cover projective line with coordinates U and V. So U and V are functions of Z and W. Well, we can construct such map that for all is it a good idea to write here? Oh, everything is clear, yes. For all K points except, for example, 0, 1 or 1, 0, let's not mind. This pair maps to our point U0, V0. And for the remaining point, which we called 0, 1, it maps to our non-trivial pair, which gives us element of order Q plus 1. Then we have U and V depending on Z and W. We can just put this into our first transformation, and then for each fiber defined over K except a fiber corresponding to 0, 1, we will have trivial map. And for this remaining fiber, which is smooth, so if we have 0, 1, then we have just equation without Z. This will be a smooth conic. It has Q plus 1 points, and the group transitively permutes this set. So, applying this map and this map, we construct a birational map of this quadric, which acts trivially on the set of Q or K points, except one orbit of length Q plus 1. It's an odd permutation. Is it clear?
So here we crucially use that Q is odd itself, right?
Yes, yes, but for even Q, it's quite similar. Then we pass to construction for Q equals 2, and then we say about what problems with Q equals 4 and the other.
But if you apply this construction to Q equals 2, then it gives you an even permutation, right?
Yes, but we can...
Because a cycle of order 3,
so
you get a cycle of order 3?
Here you see, we can start with a family, something like rotation of circle. Yes, and for even Q, we can find other embedding of P1 into automorphism group of this conic, and consider another family of automorphisms. The idea is just the same, and for example, in Cantat paper, it wasn't even mentioned these formulas. It just was written the idea of method. So this part is quite to have more explicitly. It's not a problem.
And just in case, now at the moment we're discussing the construction by Cantat, not from the longer recent paper by
the same. So in Cantat, this construction is given. Maybe there is a small mistake, but I'm not sure. Since in Cantat it has order Q minus 1, and it has 2 fixed points defined over Q. But this was quite strange, since if it has 2 fixed K points, then problem with these points, which all lie on this conic 2, it maps something in other way, I think. So it's quite the same. So Q minus 1 order was in Cantat paper, and Q plus 1 in paper by the other authors.
And another question, before you go further, this non-birational theorem by Liszt and somebody else, was it only about P2 or?
Not only about P2, it's about n dimension.
And the assertion is just the same in n dimension.
Yes, yes. And some results in the paper of K.Lai and followers concerning results in n dimension. For example, that all projective transformations are even. It's quite easy to prove using just certain generators of our linear group and see that both generators are even almost for every case. Well,
but what do we know about, say, birational transformations of P3 over a file field over some nice characteristic or odd characteristic?
Well, actually, for odd characteristic, this method, which was given by K.Lai, it seems that it works in for any dimensions. Well, I just look down a remark to not to make mistakes. Yes, he said that the proof is the same height dimension. So he just consider a quadric, consider such kind of bundle, conic bundle, but not over P1 or over a projective space of certain dimension. And then just in the same way maps maps our projective space underlying base of the conic bundle into automorphism group and puts in all K fibers trivial automorphism except one when it acts as permutation of Q plus 1 elements. So it's works in any dimension. It's a general construction. Yes. Well, so let's finish it. Now we have such a map, and we want to induce a map of projective plane. How we will do it? We consider a stereographic projection.
And just in case, is this parity, I mean, the permutation being odd or even, is it birational invariant? Like if you find this out on some model, some birational model, and then go to another birational model, is it preserved?
Well, I give an example where it isn't invariant, where we'll consider case of characteristic 2. Yes? Then it will be not invariant. So, what is the remaining part of our proof? We have element G here, which acts as the way we considered before. And now we can consider stereographic projection from N to projective plane. This projection is just blow up of N and then blow down of this pair of conjugate lines. So we have a system of conics passing through two conjugate points on P2 and with a given direction, something like this. This is the second singular fiber, and here we blow up the point N. Then these points maps to line passing through two blown down lines. What can we say about it? We can say that almost all points are fixed. So this is on these lines, on these conics, except one distinguished conic when we have a permutation of order q plus 1. What about this line? This line comes from the point N, and on the fiber containing N, the group acts trivially on each of these two lines. Therefore, it also acts trivially on the tangent space of this point. And thus, when we blow up this point, we have a trivial action on the exception divisor. So all these points are fixed to K points. So now we can see that we construct odd permutation, since it acts trivially on all points except by orbit of even length, of length q plus 1. Well, and the second thing about this construction is actually that it doesn't preserve collinearity. So if we consider a line passing through any 2 points, red points, and one more point on this line, then when we act by our group, these points move here, these points move here, and a line can't have more than 2 common points with a conic on plane. So this point will not be on line passing through these 2 points. We see that it doesn't preserve collinearity. Moreover, for such construction, even if we construct a map of quadric of this, which acts non-trivially on one K fiber, then the corresponding map on projective plane doesn't preserve collinearity. So actually, almost the same construction shows that the image of birational permutation in the permutation group is at least alternative subgroup. Well, and so now we prove that for odd Q, the image is whole 7-parameter group, and we can pass to the case of characteristic 2. Let's start. So, well, I consider the case of Q equals to 0, but for other Q, the construction is quite common. So now to write down the equation of this quadric, we should do something more. Since in characteristic 2, there are always problems with quadrics, conics, and so on. But we can write down something like this. With the same projection. So for this projection, if Q equals 2, we have 3 fibers defined over K. The fibers corresponding to Z equals omega or W. W equals 0, it's singular fibers. Pair of 2 conjugate lines. Singular fibers. And on these fibers we have 1 point on each. And the third fiber defined over K is the fiber z equals to 0. And for this fiber, we have that it's non-singular, it's a smooth conic, and it has 3 points defined OK. Well, what about parity problem, which Kostya asks? We can see that this question is symmetric on the interchange of x and y. Therefore, just this automorphism of finite order acts on our quadric. Moreover, it preserves our fibers, and therefore it preserves each of those 2 points of intersection of 2 conjugate lines, and also it acts on this set of 3 K points as a permutation. It's easy to check. It's odd permutation, yes? But what's the problem? The problem is that we can regularize this permutation on our projective plane. Just blow up this point and then blow down these pairs of lines. But actually, it will be not just a simple transposition, since it will be linear automorphism of projective plane over F2. And one can easily check that each involution acting on P2, regular involution, not birational, is even permutation. So for this simple example, you can see that parity is not invariant, not birational invariant. Yes? Well, but what can we do here to avoid this problem? We can do something like we did previously. So we have 2 maps which makes this conic invariant. Yes, one map is xy goes to xy, trivial. And the second map is xy goes to yx. Therefore, as in the previous case of odd characteristic, we consider a family of maps depending on variables u and v. It will map x and y to something like ux plus vy and vx plus uy. And doing something with z and w to have good action, since we can multiply u and y by the constant. Well, one can see that for u equals 1 and v equals 0, we have trivial action, and for u equals 0 and v equals 1, we have non-trivial action, which is just permutation on a conic. So actually this works in not only for F2, but it works for any even Q. But the problem is that only for F2, this permutation of 2 elements will be alone. So if Q is greater than 2, then we have even number of permutations, and the constructed map of a conic will be even permutation, and Q equals 2 is just a special case. So considering something like this, we can then parameterize, as in previous case, u and v by z and w, and put this map such that for these two fibers, the action is trivial, and for this fiber, the action is non-trivial permutation.
So the argument here is that if you are over the field F2, then any automorphism of a conic of order 2, of projective line of order 2 is an odd permutation, right? Because the only thing that it can do is to permute just 2 points and leave the third one untouched.
Yes.
And do you have the same kind of trouble if you try to do a similar construction over F2 but in higher dimension?
Well, over F2 in higher dimension, let's see. I think for Q equals 2, it works in higher dimension. Yes, and C signature is -1 if P is order, or order of K is 2. So it seems that it works in higher dimension for Q equals 2, but it doesn't work for Q4 and greater. You see that this situation, what is the reason? The reason is that when we consider this automorphism and pass through the projective line, not on conic, it will be something like this, not U, but which letter I don't use today, M. Yes, and it have order 2 for any field of characteristic 2. We can't put here automorphism of order 4, order 8, and something else. We can just consider automorphism of such kind, which gives us number of permutations of 2 elements. And for Q equals 2, we have just one such cycle. And for Q greater than 2, we have even number of cycles, so we can construct this way an odd permutation. So moreover, for Q equals 4, 8, and 16, the authors of the later papers, they used computer and checked that there are not birational permutation which maps to permutations of odd signature. So the image is actually for Q equals to 4, 8, and 16 is alternative group.
So how did they do this? For this they would need to know the generators of the Cremona group, right?
They find generators of birational permutations.
And what's the just in case? And what do we know about generators of the Cremona group over a finite field?
Oh, I think it for simple Cremona group, not for birational permutation.
Okay, let's start with the usual Cremona group.
Usual Cremona group, they I think follow Исковskих and something like that.
I think this is the same problem, Kostya, as the usual Cremona.
Yeah, but for instance, it's always the case that for arbitrary fields it's totally terrible, right? Yeah. But for relatively nice fields, like for the field of complex numbers, for the field of real numbers, the answer can be given in a reasonable form.
Well, for perfect fields, the set of generators of Cremona to K for perfect, not only finite, is given in the paper of Исковskих.
Yeah, but there the answer is like extremely huge and actually hard to apply, I would say. But we all know that there are nice fields, like for instance the field of complex numbers and the field of real numbers, where the set of generators can be written down in a short and reasonable form. Like over the field of complex numbers, you just need automorphisms and one single additional thing.
Yes.
Over the field of real numbers, you need a little bit more, but still it's like some set of generators with which you can really work. And what's about the finite fields? Do you have some, I would say, reasonable set of generators?
I think they don't use it. So.
But then how can they do it?
They construct set of generators for birational permutation using paper of Исковских and his result, huge result, and then look on the.
And so it appears to be a finite set of generators.
It's huge, and actually you see even for computer.
But huge and huge and infinite, it makes a big difference, right?
Yes, I can find it. Boom, 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 boom. They just say that they can consider set of generators for Cremona group, and they say that if we intersect this set with birational permutation, we obtain generators of birational permutations.
But I'm still missing it. So the set of generators of the Cremona group, if you just try to extract it from Исковских paper, then it's a kind of infinite.
Yes, yes, and they use his results.
How do they check it by computer if it's infinite?
They simplified it quite, but the problem in general is far from solution. You see only 4, 8, and 16, no more.
No, but I'm still missing it. So let's glue to the field of 4 elements. Is the set of generators finite if we fix this field?
Well, I can find it. Where is it? Lemma 4. Wow, whoa. Actually, it seems that it is finite. What is relations? Yes. So it will be a birational transformation of projective plane of certain degree, and thus, since birational transformations of certain degree is bounded itself.
This is for sure, but then you also need to bound the degree.
Yes, it looks like it's bounded or something like this. Since yes, it's not bounded, but the main unbounded part consists of elements of finite order, which don't give us even odd permutations.
This is already okay. This is already a good discussion. So now you said like 2 things which I don't understand. First, and how do we know that the unbounded part is of finite order? Consists of elements of finite order?
It can be chosen. They prove it. So they.
And so it's a feature of finite fields. It doesn't hold over arbitrary perfect fields.
I think I'm not sure really. Yeah.
We need you in this discussion. What do we know about generators of the usual Cremona group over the field of?
To be honest, I don't remember.
Yes.
I tried to.
Me the same. I agree with you.
Okay, and why at least
I'm not prepared, but you should prepare.
And why at least if we know that it consists of elements of finite order, how do we check that elements of finite order are not interesting here?
Well,
how does one check that an element of finite order gives you an even permutation?
They prove it. It's many pages.
But at least what's the idea? So I would possibly try to guess that an element of finite order can be regularized on one of the birational models, which
yes. Well. They first prove it for automorphism regular or the better surface equating bundles.
Okay, for the better surfaces you can go through some possibly large list and maybe check everything case by case. For conic bundles you also can figure out something, but then you said at the beginning that that this property of being even and non-even is not invariant with respect to the change of the birational model. So if you figured out that your birational transformation, say, regularized on some better surface, then you cannot return back to P2, right? If it is not
Yes,
rational.
but even Kostya, even you have this birational isomorphism typically is not unique, and possibly it gives you different parity.
Yeah, so if this property was birationally invariant, then I would be able
Yes,
to
this
at least...
is also my question. Yes, but
And I think the general trouble with this popular approach via minimal model program is that it doesn't tell you literally anything about the birational transformation.
Well,
yeah, but
I think I know the answer, but I'm not sure. Seems that it birational, maybe it's, well, I'm not sure. 1 minute. Yes, they say that it's invariant for q greater than 2. For even q greater than 2.
is it difficult result?
It's quite technical. So they start from projective spans of arbitrary dimension, then apply it. Let's see some structures.
So it's
so
But then
once
it's
again,
fine, but still it needs something.
it needs some many computations. It's 4 pages proof of this result.
and if he was
Without preliminary, it's 4 pages itself for this one lemma. So it's
and can you also comment, if Q was odd, then this parity would it be invariant?
Товарищ, нас последний иностранец покинул, прошу заметить.
ну так потому что доклад к концу подошел, начались уже это обсуждение. В принципе,
Потому что, да.
Этот самый китайский шпион, который за нами шпионил, убежал, да?
Да.
Ну хорошо.
Ну вот, в принципе, кстати, я рассказал все, что хотел, поэтому можно пообсуждать чего-нибудь.
Вот я хотел понять хотя бы на уровне идеи. Вот как вообще, ну, во-первых, все-таки, что верно? Вот если Q нечетная, наоборот, то это хреновина бирционально инвариантная четность установки.
Если Q нечетная. Вот они не задавались этим вопросом по понятным причинам, потому что для нечетного и так все понятно. Сейчас, надо сообразить, в чем там фишка. Может быть, что там может такое случиться, чего там... То, собственно, понятно, почему с Q равняет 2 и Q равняет 4 и больше так происходит. По более-менее тому, чего я показал с вот этой вот неподвижной точкой и количеству перестановочек, которые при раздутии и стягивании получаются. Если он...
А как вообще, в принципе, можно доказать ее инвариантность? Ну хорошо, вот пусть мы живем над полем характеристики 2, ну вот над F4 или больше, что называется. Вот как вообще, в принципе, можно доказывать эту инвариантность? То есть, как бы, ну, вычисление на 4 страницы, ну что они хотя бы вычисляют?
Что-то они там считают такое сложноватое.
А
То есть там
как насчет того, чтобы, если это, ну, Костя, ведь этот же инвариант можно определить на любой модели.
Разумеется, но если он
да.
не бирционально инвариантен, то большого смысла, пожалуй, в этом нету. Да, вообще на любом многообразии можно определить.
Правильно, да, правильно, но на любом многообразии. Но если он, ну, они доказывают, что он бирциональный инвариант,
Ну,
значит...
а какой статус этого утверждения? Они доказывают, что он бирционально инвариантен для чего? Для рациональных поверхностей? Или...
Сформулируйте результат.
Бирациональный вариант для того, что это бирационально. Значит, эта лемма называется она жутким образом 3.12 у них.
Ну, ладно, как она называется.
Вот, и значит, результат такой, что если есть две проективные поверхности x и y, да, и между ними бирациональный морфизм, ну, морфизм достаточно, над полем характеристики 2, притом не из двух элементов, а большего количества, то, значит, если у нас есть элемент, который на y действует и сохраняет по точке, то соответствующий ему элемент, действующий на x, имеет ту же самую четность.
Ну вот, Костик, то, что я говорил.
Ну да, вот прям вот такой.
Это нужно просто, тогда это нужно просто при раздутиях он сохраняется.
Ну и да.
При раздутиях точек, ну да. Ну и возможно там, ну да.
То есть понятно, что там бывают раздутия точек неопределенными от поля, которые нам вообще ни на что не влияют. Бывают раздутия точек каких-то неподвижных относительно действия вот этого.
Ну а тогда что вычислять? Наверное, это просто. Если это верно.
А давайте действительно его докажем просто в уме. Вот что происходит, если мы разделим голову орбиту точек, состоящие из более чем одной точки? Тогда ваш автоморфизм, вот был у нас автоморфизм, уже не бирациональный, а просто бирегулярный, да? Ну давайте для ясности, бирегулярный. Да. И мы у него раздули голову орбиту, извините, мы его раздули его орбиту, наверное. Да, орбиту.
Ну, понятно.
Но тогда ничего не влияет, Костя.
Не произошло. Не, и автоморфизм должен быть нерегулярным, автоморфизм должен быть бирациональным. Просто он должен сохранять множество этих точек. Вот.
Ну хорошо, да, это не важно в данном случае. Что происходит, если он переставляет как бы три исключительные кривые по циклу, например, да? Ну, наверное, тогда все это разбивается...
Нет, но на К-точках это никак не действует, Костя, что вы говорите.
Ну да. Как бы то, что происходит не может в
Нам нужно точку раздувать.
Нет, я имею в виду не голову орбиту раздули, а раздули орбиту, состоящую из К-точек, ну, просто нетривиальную орбиту нашего автоморфизма.
Ага.
Тогда действительно, тогда в этом случае действительно проверять ничего не надо, потому что у нас автоморфизм переставляет в каком-то количестве, в количестве n штук, вот эти вот проективные прямые, которые доклеились. Каждая проективная прямая, то есть у вас был один цикл длины n, где n либо четное, либо нечетное, неважно, а вы добавили еще столько же таких циклов, сколько на проективной... Вы его вырезали и вклеили еще столько же таких циклов, сколько на проективной прямой точек.
Ну, видимо, да.
То есть вы вырезали один цикл и добавили нечетное количество циклов, потому что мы живем в характеристике 2. В этом месте, кстати, рассуждение совершенно не сработает в характеристике нечетной. Просто катастрофически. То есть вы добавили четное количество циклов, другими словами, одинаковой длины.
Ну да. Но еще, Костя, есть сложность, если ваш автоморфизм все-таки не бирегулярный.
Ну,
нет, сейчас, секундочку. А давайте еще все-таки, но я не понимаю такую часть этой истории. Вот все-таки, нет, это я на самом деле сказал не совсем точно, потому что я, видимо, предположил, что давайте фиксим, пока все регулярно, я предположил, что у этой точки, у точки z орбиты нетривиальный стабилизатор. То есть эта перестановка никак не действует внутри одной исключительно кривой. Но давайте рассмотрим, наверное, другой крайний случай, когда вы раздуваете просто неподвижную точку автоморфизма.
Да.
Тогда вы выкинули одну неподвижную точку, на четность это вообще никак не повлияло, на дополнение к этой точке четность такая же. То есть вам надо доказать, что на исключительной кривой индуцируется четная перестановка. Но это Андрей нам, кажется, уже почти объяснил. Сейчас, Андрей нам это объяснил.
Чего я там объяснил? Я объяснил для конечного порядка. А то вот как она, как бы элемент-то, он не бирегулярный, он как бы действует бирационально, вот как он представляет на вот этой вот исключительной дивизоре получившейся точки.
Мы модельный случай разбираем.
Мы хотя бы прикидываем просто, как вообще это могло бы доказываться. Нет, мы не хотим сейчас то, что они там год придумывали.
Сейчас, да.
Хотя бы, это имеет шанс быть верным.
Если мы раздули эту точку, то на исключительном дивизоре он действует вполне себе бирегулярно, а значит, перестановка четная, просто потому что в PGL2 все перестановки четные.
Мы знаем теорему, да, что в PGL2, вообще в PGLM все перестановки четные, да? А что, как же так?
Это не достает. Нет, там все сложнее. Там
А как же так? Что-то я вообще ничего не понимаю. А что в PGL... То есть действительно, в PGL2 от F2 есть такой элемент, который меняет местами две точки, больше ничего не делает.
Угу.
А вот в PGL2 от F4 такого элемента нет, да?
Ну, потому что вот я говорю, что он меняет местами не две точки, а кучу пар. И вот в этом-то и загвоздка.
Да, здорово, очень хорошее наблюдение.
Отсюда и все проблемы.
Ладно, хорошо. Нет, ну здорово, потому что как бы куча непонятных мест в такой практически олимпиадной задаче. И куча недобитых мест в такой практически олимпиадной задаче.
Не, прикольная задачка, но вот я ту часть, которую рассказывал, я долго осознавал, особенно с неподвижной точкой, но вроде осознал. Вот там дальнейшее я уже меньше смотрел.
То есть, что же действительно здесь остается недодуманным? Верно ли, что... То есть их вычисления показывают, что, скорее всего...
Скорее всего, они АН-ки.
То есть, начиная с поля F4, для всех четных характеристик не бывает нечетной перестановки, индуцируемой вибрационным преобразованием, да?
Ну да.
И, ну, а для P3 и выше вообще никаких даже гипотез нет толком.
Не, ну что, для P3 и выше есть ну, в смысле, есть результаты для нечетных и для уравнивается 2, а для остальных понятно, что там все еще. Не, у них, кстати, между прочим, есть уже результаты про старшие размерности, в частности, они там для ПЖ или всех показали, что они все четные. Вот. Что-то еще.
А это в той же длиннючей статье Циммермана компании, да?
Да, не, вот там рассуждения, те, которые общались тривиально, они дали их в общем виде заранее, потому что, ну а что их? Как бы какая разница, давать так или не так. Как бы та пожелика двумя элементами порождена, пожелика двумя элементами порождена. Какая разница, про размерность 2 доказывать или сразу про все? Конечно, лучше доказать сразу про все, они и доказали. Доказывать особо там ничего, все удобно, красиво, хорошо.
Здорово, здорово, очень интересно.